Carly will be presenting, our very own Carly Huitema will be presenting schemas in the decentralized data ecosystems of research. So looking forward to hearing this.
Today I'm going to talk about the research data ecosystem and our work at Agri-food Data Canada on data schemas. So first, a bit of a primer for people who maybe aren't familiar with the research data ecosystem in Canada. Research in general is a very decentralized ecosystem. The research groups are very independent. They can be guided by best practices and norms, but these larger pushes to say you have to do it this way is often very slow behind. The research in Canada is supported and internationally supported by infrastructure projects that are both large scale and small scale. So you've got all different from national, large integrated with international participation down to an individual lab might run some piece of infrastructure for research. Very heterogeneous, and the trust is because the idea is that things are public and reproducible. Public as much as can be because of like human health data, for example, is supposed to be maintained privately. And within the research data ecosystem, incentives can often be conflicting. Like because of this publish or perish mentality, that's highly valued, but then doing very like well-documented data sets and stuff like that often doesn't appear in incentives. And also to think about that research in the data ecosystem is long-term. So some of these repositories for storing archival data have like funding planned for 50 years to hold that data sets. And certainly like at the University of Guelph, we're pulling out old paper data and digitizing that from like 100 years ago or so. At Agri-food Data Canada, then, we're a project at the University of Guelph to improve research data management. Our funding is drawn from multiple Canadian sources like CEFREF, Genome Canada, Compute Ontario, OMAFRA. And what we're doing is we are working at the level of the user. So we're working with researchers directly to improve and help make their agri-food data fair. I'll get into what that acronym means in a moment. But first, I wanted to show you a part of the ADC team. This is the Semantic Engine team. We have had some co-op students in the past, and we have two key developers, Matthew and Stephen, who are doing all the work that you are going to see today here. But of course, there's a broader team at Agri-food Data Canada doing like historical data management, governance applications, and so on. But today, I'm just going to talk about our work with the Semantic Engine. So making agri-food data fair, and the FAIR acronym is the principles that data should be findable, accessible, interoperable, and reusable. And I'm going to argue today that the FAIR principles fit very well with any kind of decentralized data ecosystem. So if that's one takeaway for today's meeting today, it's that the benefits are FAIR are good principles for ecosystems. Findable is the ability to identify and find resources as well as their context. If it's accessible, that once found, you can access it with permission and use it. Interoperable, certainly lots of our work at Trust over IP is about how to ensure interoperability of standards, including vocabularies. And reusable, that there are licenses and provenance and other things that help make this data reusable. So good principles for any kind of ecosystem. Data on its own does not speak for itself. What data needs is that it needs to be placed into a context. It's when you have all these extra pieces of information that you can start to understand and apply the data in a way that is understood within its context. And what we're doing at Agri-food Data Canada is we're developing a suite of tools that we call the Semantic Engine. The Semantic Engine is going to help researchers write contextual, machine-readable data schemas. What is a data schema? When we have a data set, so I'm talking about tabular data, like spreadsheet data, CSV data, something that fits into a table. We have a data set. This is commonly collected in research, and we're going to have a bunch of attributes that we are collecting information about. And if we list all of those attributes and describe them more fully about what kind of data is being collected, we call that collection of information a schema. So the schema is describing the attributes in a data set. At the semantic engine, the language for writing a schema that we've selected is something called overlays capture architecture. So that's being developed by the Human Colossus Foundation. It's an international and open standard for documenting schemas. And that's the language of schemas that we are using in the semantic engine. So why did we pick OCA, and what are some of the benefits that there's benefits and trade-offs of everything. So with OCA, there are two main characteristics that we really appreciate. Number one is that OCA embeds digest. So people here at Trust over IP are probably familiar with carries and ACDC and Caesar. So we are using the SEDs of Caesar specifically as our identifiers. And I'm going to talk a bit more later about just how great I think derived identifiers are in a decentralized ecosystem. The other feature about OCA is that the schema is organized by features, which is going to enable task-based governance and interoperability. So let's get into these characteristics. We use identifiers to help you find things and to build context. For example, at the Royal Tyrrell Museum, they've got thousands and thousands of bone samples. It's a famous paleontology museum in Alberta, and they've got libraries of fossils. And you want to know which tooth belongs to which dinosaur and what information has been collected about it. We have different ways to develop identifiers. The first one that I'm going to mention is assigned or name identifiers. It's very common. We're certainly all familiar with it. And that is where some kind of governance body is going to create an identifier for some specific object. And they also might add additional metadata to help describe the object. And what that governance body is going to do is they have to create what I've called down below the lookup table. They have the identifier and then its location where you can go and find it, and maybe some additional metadata. And the point is that everything depends on this lookup table. If you find any item and you want to know what's its identifier, you have to verify it in the authoritative lookup table in order to find what the identifier is. It might give itself a fake ID identifier. Certainly ChatGPT likes to stick them in all over the place. But the only authoritative source is where is being held by the governance body that controls that identifier. So you have the assigned identifiers, you've created your lookup table, there might be some metadata associated with it. So at the Tyrrell Museum, I would go into the local database, I would pull up the tooth identifier, and I'd know that I have to go to cabinet 65, drawer 5, and look through the boxes until I find it. In contrast to assigned identifiers, we really like derived identifiers. They are really important for reproducibility and authenticity, because with a derived identifier, what you're doing is that it works for digital objects. And what you do is you are calculating the hash, using a hashing function to calculate the digest that is directly derived from that digital object. So I have an example down below. You put the digital object into your hashing function, out comes a digest. And that is a unique fingerprint for that digital object. And you can't go backwards. So anyone, anywhere who finds a digital object is going to be able to calculate its derived identifier. And I would argue that in a decentralized ecosystem, derived identifiers are key. And if you liked them, you should have put a digest on it. Now, when you want to resolve your identifiers, for an assigned identifier like a name or whatever, since the governance body is the only one that has the authentic table that matches the identifier with its object, only that governance body or its delegate can host a resolution service. Nobody else can create a verified resolution service. And this is great as long as, and efficient, as long as your governance body never screws up, doesn't get taken over by something hostile that wants to destroy the information, and it has the funds in order to preserve it throughout time. Now, with a derived identifier, anyone can calculate derived identifiers and build a resolution service for those derived identifiers. So, and if you have an existing resolution service for named identifiers, you can go in and throw in derived identifiers, like you can start substituting right away. And the other thing that's nice about using derived identifiers is that they can be hosted anywhere in multiple locations, because the problem with with named identifiers is that you have to resolve it in order to find the single authentic copy. But with a derived identifier, you can go around and look and calculate and say, oh, in this location, it's this, and in this location, it's the exact same thing. And anyone can then therefore build a resolution service, and anyone who's using it can verify that that resolution service is resolving them to the correct external resource. Eric.
Sorry, what you mentioned something about transitioning from did you say that? Sorry.
Oh, yeah, just that if you have the functionalities, if you have a lookup table that's using identifiers, there's
Yeah.
no reason that your identifiers couldn't be, that you could start to use derived identifiers in your lookup table.
So you would use the identifiers as they exist, as they were given by that governance authority,
Yeah,
and then they were, and then you have to tell which hashing function you're going to use to
yeah,
generate these
yeah,
self-certifying identifiers, and
yeah,
then from there those can start circulating and be
yeah,
resolved without this central governance authority.
yeah. And
How? Did you
yeah.
how? How does that work again? That if how does the resolvability work again? If
Yeah, so there's going to have to be some kind of lookup table. Like you're going to have to use the identifier, and then somebody's going to have to point you to one or more locations where they can go off and find that object.
okay, so you still have to have a lookup table,
If you
but
want to resolve anything.
it's not centrally managed.
Yeah. Yeah,
It's
it's not centrally managed, and it can be rebuilt. If your lookup table gets blown up and you go out and find the pool of objects, you can then go back and regenerate the legitimate lookup table.
okay if you know that. Okay.
Because you can conceivably calculate the derived identifiers. And if you're interested in this, there's currently an ongoing proposal about URNs for SEDs for derived identifiers to try and harmonize standardized naming. And that's an ongoing chat in the ACDC discussion at Trust over IP. So on to the second feature about schema, OCA schema specifically, is that I said that it was organized by features. So here I am, I'm looking at a larger table of a schema. So I'm describing the different attributes inside the schema, and I have all the different types of features for each of those attributes, and it's a table. But when you're serializing it as a schema like JSON LD or JSON schema or XML, anything, you don't represent the data tabular. You have to go through and list either row by row or column by column. So schemas that are what I call attribute by attribute schemas are going to be JSON LD, XML, JSON schema. And what they do is that they serialize the schema. They say, for this attribute, here are the features. For the next attribute, here are the features, and so on, all the way down. OCA instead does that column by column, so it's feature by feature. So it'll say, for the label attribute, here are all the labels. And then for the information feature, here's all the information. So that's how it gets serialized linearly in this, in the text file that's going to be written to express the schema. And what's important about that is that each one of those chunks can be hashed and given an identifier, okay, a fingerprint identifier, a derived identifier. So what you get in OCA, or you could do this with anything, is that for each sub-object of that schema, you're putting fingerprints on each one. And that means that you can start to have governance to say that, oh, for fingerprint X, which is representing some specific feature like French, only Scott is allowed to edit that feature, something like that. So you can talk about those pieces specifically when they are given derived identifiers. And how OCA is managed is that it's optimized for feature management. So you can add in and out languages, you can swap units, and you can see which parts of the schema have been changed and which parts of them remain the same. So what I mean by that is that, like in an attribute by attribute schema, each little block, like I said, in an attribute schema, it's row by row. So if I add a new feature, I'm going to be changing every single row, and I'm going to be changing every single fingerprint. And so anytime you add a new feature, it's going to disrupt every bit, every sub-chunk of your schema. And I'll note that this is hypothetical because currently no attribute by attribute schema language embeds digest, but they could. In contrast with OCA, because it's column by column, when you're adding a new feature, you're appending to that listing of features. So those other fingerprints don't change. And what it means is that it's easy to like mix and match different chunks and being able to tell, oh, they changed the French language, but they didn't touch the units, or they didn't touch the meaning of something. So that's the benefit of the architecture of feature by feature, which is in OCA. Now at Agri-food Data Canada, we went a little bit beyond straight OCA. We've wrapped the OCA schema up in something that we call OCA package. And what that means is that we have in OCA package, we've got two basic chunks. One is the standard, which is slowly evolving, follows the human colossus standard as it's published, but there are new features that haven't been described yet. So those ones, the invention, the very specific one-off weird case, and the developing standards, they go into something called extensions. And the idea is that slowly things, as they become standardized and accepted by the community, can move into the core of the schema. And I show in the picture, right down below, you can see this big hierarchical tree. I've talked about OCA schemas only in the context of tabular data, but OCA can also be used to describe these larger hierarchical table of tables structure. That's with showing there with the dependencies. So all of our work with the semantic engine is only for a flat table. It's not for hierarchical, but the language of OCA itself supports hierarchical. So on to our actual implementations for the semantic engine. So like I said, we are working with the level of the researcher. So what we wanted to do is to be able to tell our researchers, who are the people who are collecting the data and who best know how to describe the data at the time of collection. I like to give an example. One of the example data sets that I often work with is this chicken gut example that I found somewhere that was given to me from some published repository. And it's got an attribute called glucose. And I have no idea how they're actually, I'm not a chicken gut expert, so I don't know how they're measuring the concentration of chicken gut glucose. Like, are they taking a chunk of it and rinsing it out and measuring it? Like, is there some kind of common chicken gut glucose measuring protocol that everybody knows about, but only in that specific subdomain? Right? So those people that know that level of detail should be the ones that when they write their schema, then they can say the glucose was calculated according to protocol reference such and such, briefly, this is the description of it. And then when I get their data with their chicken gut glucose measurements, I would actually know what they were measuring. So with the semantic engine, we have semanticengine.org. Anyone can freely access that. It's a web app. And the idea is that it should be self-teaching so that you can go to the semantic engine and watch the little video about what a schema is and go through the little tutorial. And on every screen, there's help screens. And then you can start to write your own schema. Eric.
Sorry, could you just stay on that little example for just a second? What is different now that you can understand the schema that you couldn't before?
Yes. So absolutely, people could have written out the information that would be held in a schema. It doesn't happen as often as it should happen. And it's documented inconsistently because there's not like this set plan of how one would go through and document things. And certainly whatever people have been writing for the most part has not been machine readable. Like we had a student who we showcased this and they came up or wrote an email later to say, oh yeah, they had been wanting to document their schemas and they had done all this work looking up like JSON schema, and all of a sudden they're having to learn how to write in JSON, and they don't know, they have to learn the syntax of JSON schema and everything like that. So it was too daunting of a task. Most people, when they do write it out, they write it out as like a text file or something like that. So this the semantic engine, what its point is that it walks you through, oh, I didn't think to write out a more eloquent description, or I didn't think about writing the units out formally or something like that. Maybe I totally, that slipped my mind. I forgot about it. And also at the very end, you're going to be getting a machine readable version of the schema. And then we have a bunch of tools that are taking that in and reusing it to help the researchers work with their schemas, so that they gain value from having taken the time to write a machine readable schema. So here we are. I mean, I can demo it as well on the web page. I love demoing because that's when I find all the bugs. So anyway, so here we are going through a self-directed schema writing. So this is on the web page. You can see that you're being prompted to say, oh, what are the units? Is this a sensitive variable or not? There's my chicken gut glucose measurement and the help videos that we have written as well. And after you've written the machine readable schema, what you can do is you can reuse it. So we have other tools available on the semantic engine. So you can drag and drop your JSON version of your schema, and you can say, generate for me a data entry Excel, because many of our researchers like to enter data in Excel. So now what you get is that it automatically creates this schema where it has the data entry sheet with all the headers that you had already laid out in your schema. So now you're harmonizing your header names and stuff. When there are lists that you have to pick from a very specific, like in Canada, we might say, oh, you have to pick from one of the provinces. So then everybody's writing like, oh, one person calls it British Columbia, the next one calls it BC, the other one calls it B period C period. So you're getting all these different variations of data entry, but when you leave it with an entry code, you can have more standardized provincial name selection. And then this data entry Excel has a second sheet that we call the schema description. So all the information that you've written in the schema is reproduced on that description, so that when you're moving that data file around, you've never lost the description of the data. And it also has the set identifier of the schema, so that you could go in the future and find it again if you just had this Excel sheet. Eric?
Sorry, I'm the only one asking questions. Sorry, everybody. Jump in. If you go back one slide, so here is this specific to how, if I'm doing chicken gut glucose, how does this engine know what to walk me through? Is it just say, I'm going to be exhaustive and you pick, or who's doing this?
Yeah, it has back to that research example of its best practices and recommendations. So the engine is always the same. Here we have the most basic parts of the schema, and then on a later screen you can go through adding additional features like cardinality or required value and stuff like that, or you can write more descriptive examples. So the other thing is that it's an editor for schema. So after you've written a schema, the machine readable JSON, you can drag it back in and start where you left off. So your supervisor said, hey, that schema was great, except how did you measure glucose concentration in the gut? Can you go back and write those details in? Then you can take your schema and edit it and then add to it, stuff like that.
Okay. Right. So yeah, it's sort of helping. It's helping them do the work that they should be doing, but it's too difficult. And okay.
Yeah. Yeah, and then it's often not standardized, and people are like, well, I'll give it my best go, and they did it once, kind of thing, and yeah, so this is definitely helping standardize. Neil?
Yeah, the observation here, being an old metadata guy from analytics days, this always struck me as a way to add metadata across your entire data set. So someone's got something crude that all they have is type, right? So you can come in after the fact without disturbing that and say, okay, I'm going to add this additional metadata as a component, right? So I can extend it without having to, because I mean, databases, you look at what you get in your standard flat database, right? About the most you're going to get, I mean, sensitive is not a metadata you're going to get about a property,
Yeah.
right? That all you're going to get is maybe units and, type. So this is a way of extending that so you can do it. Now, I would assume that if you were looking at more just a flat table, you could also say, okay, I've got two tables here. Here is the metadata about that relationship.
Yeah,
Right.
the metadata of the relationship, not to get into too deeply, but within the OCA language is that you're going to be referencing a subtable and then and having like a certain cardinality for that subtable and stuff like that, and descriptions about that. So I've talked about, now you've got your machine readable schema, and for our researchers, they find it very handy to get these data entry Excels, especially like if you're coordinating, say, you're going to do beehive colony measurements across the country in January, next year. You can generate these data entry Excels and share it with all the different team members across the country, and everybody's going to be collecting the same data, and you're going to be writing details like, dead bees are only counted when they're in front of the hive, not when they're found within the hive, or like whatever the specifics are about how you're calculating or counting. Stephen?
Yeah, that's pretty interesting stuff. Regarding the rules behind it, you were just describing, how many bees or how do you count it, so on. That's the governance behind it, or the if then else's when you validate it.
Yeah.
Is that in the OCA, the business rules?
Some of it is the if then else's. So that's one of the reasons that we went ahead with developing that OCA package, because if you wanted to start adding more complex logical validations to it, like it starts to become more specific to the system that you're working with. So you can write your extension overlay to hold that information. And in the future, if it becomes standardized and lots of people using it and liking it, that's something that can then be gradually migrated over to be more of the core specification. So that's another reason why we like OCA, because any kind of development like that is going to be a feature, which is going to not change the said values calculated for all the other features, or for every attribute and stuff.
So can you switch out I don't know if do you call it governance or the rules behind how to enter the spreadsheet? Can you switch it out depending upon maybe your jurisdiction or anything like that?
You'd have to, not for our not for our more simple use case, but you could. So all of this stuff is open source. It's called OCA Composer. There's a GitHub repo. And then if you wanted to add like more functionalities around if then else statements for logical statements for kinds of checking and stuff like that, and then adjust the data entry Excel in order to handle that kind of thing, absolutely. So, but we don't have that functionality.
Okay.
Yeah.
That's pretty cool nonetheless. Thanks.
Yeah. So then what we're also doing, another tool that we have for, you've generated your machine readable schema. And now if you're on the back at the semantic engine, you can use it not for generating a data entry Excel, but something that we call data entry on the web. So you're going to add your schema, and you may optionally upload a data set, Excel or CSV data set. And then it has a data verification engine that verifies the data sets according to the rules that were described by the schema. So back to our example, like if you were working across the country and everybody was collecting their bee data, and then you could say, oh, before we're going to collect everything together into our giant table and start doing analysis, everybody run this through the data entry web and verification engine, and just checks to make sure that there's no inconsistencies before we combine the data. So that's another tool that we're showing the advantages when you have a machine readable schema, that then you can start to use it for other tooling to automate processes and stuff like that. And we did have, it's out of date now, but a similar kind of engine, but for Python, because we're thinking, oh, if you're wanting to do data ingestion into machine learning models or something like that, you could ingest the data in parallel with the schema, use the schema to do your quick verification before it continues on through your pipelines. I just wanted to show this. It's coming up soon. That was that feature about being able to co-author schemas because different people are contributing to different features because of that governance ability, because of the feature organization. So this is the user interface for, we've settled on the base of the schema, and then I've handed it off to one group because they know the units better, and then another group is going to do the translation, and then in the end we decide how we're going to combine that all into one schema, because because each feature can be inserted, picked and chosen from two different schemas in order to co-author something. So that's just a quick example of why you have that feature organization. And then finally, what we've done at the University of Guelph is we have a bunch of people that are always like, oh, I want to know what other data people are collecting. And other groups are like, I don't want to share my data because, I'm not done the research on it, or it's private information, or I have this agreement that I have to keep it private, or health data or something like that. So what we've promoted is the ability, so you still have your machine readable schema, and we do have a text rendition of it. So you don't have to read JSON. It comes out instead as a plain text, and that's formatted for archival purposes. It's not the prettiest thing to look at, but it'll be readable in 50 years, so that's suitable to go into these long-term repositories. But for active data, you can generate a markdown version of your schema. You drag and drop it in, you get the markdown version, and this is just something that we spun up real quick in GitHub. GitHub has GitHub Pages, which lets you render a GitHub repository as a nice readable web page, and all those schemas then show up in this example. So now all the different research groups can look to see what other people in their, in this larger research program, what kind of data they're collecting, and then looking for harmonization opportunities, or, oh, I didn't know you were also collecting soil data. We wanted to work together on it and stuff like that. So these schemas are for more active data, like this GitHub repo is not going to live for 50 years, or maybe it will, but it's certainly not planned for that. But that's for active data research. Now, we've also been working with our schemas at ADC in order to try and integrate deeper into Canadian research infrastructure. So looking, we have our active data parts where we're working, and if you're publishing a paper, you would say, I collected the data according to schema set identifier such and such, so that everybody who reads the paper can go out and find exactly the schema that you were using, and they can verify against the identifier that you published. Okay, but then to deposit those schemas, also to make it more accessible long term, going into research data repositories, such as, like in Canada, we have the Borealis repository, which is this federated Canada-wide interlinked repository. And then we're also taking advantage of the existing infrastructure of research. For example, we have Lunaris, which then goes through and searches all these repositories. So when I deposit a schema into Borealis and I give it a DOI identifier, which is an assigned identifier of a schema which has a derived identifier, but anyway, I can deposit it in, I can get an identifier for it, and then it will also show up in Canada's Lunaris search engine, which is searching all kinds of different academic repositories. And also, we've been experimenting to get all those variables, all those different attributes to appear up in Odyssey, which is another search engine of different multiple repositories. And in fact, globally, all of those repositories are further integrated together because, for example, Europe's OpenERROR search engine will also find schemas that we've written and published within the Borealis system. So here's an example of this milk parlor data schema that we wrote that's showing up in Odyssey. Good thing, I hope Michelle's still here because she knows the details about how it went in more than I do. But you can start to see at the variable level the different attributes that I had put in my schema as they appear here. And then here is an example of that same schema when I went to Europe's Open Air Federated Search, and I could pull out the same schemas that I had deposited back in the day at the University of Guelph's Borealis repository. So towards the future, what ADC is continuing to do is we're going to continue to integrate and adopt different research infrastructure. We want to add digest as identifiers to more objects and try and integrate these as much as we can into research infrastructure, and continue to make other machine readable standards such as cataloging or policy rules about data sets and stuff to make that more accessible via better web apps such as the semantic engine. And of course, trying to add digests to everything, which I think are fantastic identifiers for these kinds of research objects. So how to follow our work? We're at Agri-food Data Canada. That's the root of all our work that we're doing. The source code of OCA Composer and OCA, the package standard, and more is available on our GitHub repository. The tools themselves are available at the open website, semanticengine.org. And of course, you can reach out to us with any ideas, bugs, comments, or collaborations, and participate in the open standard at Human Colossus. So thank you very much. And if there's any other questions, I'd be happy to take them.
Great. Yeah, 9 minutes for questions. So just one. I mean, this is open. Is this sort of the open data? This is where open data it's not a movement, but it's in science where the need to share more data, et cetera. This is really gels with that, right?
Yeah.
And how do you deal with IP?
So again, what we're doing here is schemas were first of all, the semantic engine, it doesn't upload it to any system. We don't have a back end where we collect everybody's schemas and stuff. It's a web app. It goes via API to get transformed, and then it comes down. And because we're not interested in hosting and keeping everyone's schemas, but also note that schemas themselves are generally much more accessible than proprietary data sets. So one of our arguments is that, you might have restrictions on proprietary data sets because other people own the IP, for example, but you could make more available the data schema, which describes the data, because if you have something and you're interested in finding collaborators who want to use it or anything like that, you can make that data available via sharing the schema instead.
Is there is there anything in the schemas that helps, because the governance is part of this, right? You said that it's you can govern at a sort of a chunk level.
Yeah.
Can you embed sort of IP, don't share this data outside of,
Yeah, so we have not built that technology in, but it is buildable. Because, well, certainly for governance of the schema itself. And then with regards to the data, if you recall, we had, when you're authoring the schema, you can flag that, you might say that like the farm location data is sensitive data. So we don't have any controls about that. But if you were building a pipeline, say internally, when it reads the schema and it detects that there's sensitive flags on the data, then internally you could have it say, you're not allowed to export data that has sensitive markers in it, or now this goes into the anonymization pipeline or something like that. So this is a way to help people manage sensitive data within their data sets, but we don't have a platform for holding your data, so we're not taking advantage of pipelines and stuff with for flagging data, but that's certainly a possibility within the schema.
Okay.
Carly, do you do anything with identifiers for the people entering?
No, we do not have any identifiers for the people entering. So I've got a whole other a whole bunch of other plans, which include things like because after you've created your schema, there's very minimal metadata about that schema. So what you really need is I think with everything thing that's created, you essentially need two other parts. You're gonna, as at a minimum, but you're gonna need some kind of larger cataloging metadata, which is gonna say who the authors of the schema are and so on. And yeah, I think you're also going to need some kind of policy metadata associated with whatever you produce. And the policy is going to, usually when people are writing schemas, their policy is going to be fairly simple. They're going to say it's a Creative Commons by attribution or something like that, some kind of basic Creative Commons license. But of course, you could make more complicated policies for, so I'm talking about policies for the schema, and then of course you could have the policy for the data set, which is different, right? So the schema might be very open and accessible and have a very liberal policy, and the data set could be a very restrictive policy that, oh, it's for people who are only participating in this particular health sharing data network, and it has these retention rules and anonymization rules and citation rules, etc.
And what do you do about versioning the schema? Like you said, you can add a feature like an OCA layer.
Yeah. So exactly. It's nice that you mentioned this. So a derived identifier does not handle dynamic content. So you're going any kind of, a derived identifier is fantastic for the snapshot of the item at that time. And then when you're talking about versioning, you're talking about dynamic content that has to be updated over time, and only by the person who can officially declare the next update, right? Because I can go out and say, oh, I'm ISO 13945 specification version 3. You know, just because I give it the name, nobody cares. They want to know, did ISO actually release the next version 3? So that those kinds of rules, if you're that kind of thing is either going to be managed by, you're going to have a governing or authority who is going to manually accept and let you append to a growing list of version 1, version 2, version 3. Or the other way to handle this kind of updating content, this dynamic content, is via a decentralized identifier, of which you're going to have to pick. And that's where you hopefully are deriving your initial identifier of the DID from the content, so a derived identifier, and then all version appendings, it'll say version 2 is said such and such, version 3 is said such and such, and you'll have the associated governance controls that a DID has that some of us are familiar with. I know some people here aren't.
Good.
Great. 2 more minutes. Any other questions or comments?
So, like I said, it's available at semanticengine.org. You can go in and start writing your own schemas and watching the videos and reading the tutorials and reaching out if you find any bugs. And or if you see another format rule that should be there. All the format rules in this, for example, are regex expressions. And we're in the midst of adding support for like range rules and framing into ontologies and stuff like that. So the project is under continual development to improve improve and increase the number of features that one can use to describe data via schema.
Excellent. Yes, indeed. Excellent. Thank you very much.
Thank you very much for letting me come and speak.